Part 2 of lesson 1.1. We're going to talk briefly about the notation used and the terminology we used when we talk about functions and when we talk about relations. And then finally we're going to talk briefly about domain and range and do the domain and range of both a function and a relation. So, function notation is useful for determining inputs and outputs, which is essentially what an equation of a function does. For example, if the equation is in the form y equals, like y equals 3x plus 5, we could answer two questions. When x equals 2, what is y? And when y equals 12, what is x? And these are common questions that we explored in grade 9 and grade 10. So let's do them very quickly. We'll call the first one 1 and the second one 2. For the first one, when x equals 2, so we would take our relation y equals 3x plus 5, and we would substitute 2 for x and evaluate. So we'd have 3 times 2 plus 5. 3 times 2 is 6, plus 5 is 11. So y would equal 11. So the answer to this question, when x equals 2, y is equal to 11, would be the answer. And that's how we'd express the answer when substituting a value within a relation. We can do the same with given y. When y is 12, so y equals 3x plus 5. Now we're looking for an x value to answer the question, so we'll replace y with 12. And we can do some rearranging to solve. Start by subtracting 5 from both sides to get 7 equals 3x, and then divide both sides by 3 to find out what x is. So to answer our second question, when y equals 12, x would equal 7 over 3. Now, using function notation, how would we ask the same questions? Well, the first one, it's when they're giving you the input 2. We would want to figure out what the function is, or what y is in the relation. So the similar first question would be, what is the function at 2? And we would solve it the same way, except when we write it, we would replace the x in both the f of x and on the right side of the equation. So it would look like f at 2 equals 3 times 2 plus 5. And we know from the math above that it's 11, so the answer would be the function at 2 is 11. That's how it would read. How would we ask the question when we're given y, or when we're given what the function is? We would ask, what is x when the function is 12? And to solve that, we would replace f of x, the function, with 12 and solve. So we'd say 12 equals 3x plus 5. And we know from our example above that the answer for x is 7 over 3. So to answer the question, we would say when the function is 12, x is 7 over 3. We can do domain of range of both functions and relations. So the domain of range of a function or a relation depends on the type of function or relation. Domain describes the restrictions on the input, whereas range describes the restrictions on the output. And we've reviewed domain and range already. But let's give the domain and range and use proper notation for both. So first we have to identify whether it's a function or a relation. And since our first graph does not pass the vertical line test, we have a relation. So we're going to write our domain and range using x and y notation, whereas our second example does pass the vertical line test at every point on the graph. So we're going to use x and f of x notation, because we're going to call this function f of x. Okay, just correcting here my handout. Instead of I for integers, we actually use Z for integers, and then we use a different type of looking R that looks more like the N for natural numbers. So just a little correction there. But let's look at the domain. The domain describes all of the x values that this relationship can take. And if we look, there's no graph to the left of -6, and there's no graph to the right of +6, which means that our domain is between -6 and 6. And since it's connected with a curve or a line that's straight with no breaks, we know that it's not integers or natural numbers because decimals are included. So we know we're in the real number set, and we know that it's every possible number because it's connected with no breaks between -6 and 6. So our domain, which describes x's, would be x belongs to real, because we're in the real number set, such that x is greater than or equal to -6, less than or equal to 6, because we're between -6 and 6. And notice we used x. For our range, very similarly, the maximum value is 6, the minimum is -6, and we're connected with a curve going up, so we have everything in between. We also don't have any breaks, so that means we're in the real number set. Since this is not a function or relation, we're going to use y. So y belongs to real, such that y is greater than or equal to -6, less than or equal to 6. And that's our domain and range, using x and y for the relation. The radius of this is 6, so if we were to write an equation, it would follow that x squared plus y squared equals 6 squared, which is 36. So that's our actual relationship there. For a function, we use the function notation, so we use f of x to show that it's a function. We could use y, but we want to be as specific as possible, so we'll use f of x. Our domain describes the x's, and since we're connected with a smooth curve, we know that x belongs to real. And we basically, well, we can assume that it goes all the way to the left and all the way to the right because it goes off the graph. We have every x value that it appears except for whatever's in this gap in the middle. And I can tell you that this graph does continue and brushes against the y-axis but never touches it. So the only x value that's actually not included in the domain is 0. So to write that in domain, we would just say that x does not belong to 0 and close the bracket, because it takes every other x value, and that's our restriction. For our range, since we're a function, we're going to start with f of x using function notation and write what set it belongs to. And again, because we are smooth curve going through many values, including decimals, we're going to set it in the real number set. And since it continues all the way up from 0 and goes forward, we know that it's every value above 0, not including 0 because it doesn't touch the axis, and nothing below. So that means that f of x must be greater than 0, but not equal to, so we don't have an equal to. And that's it for lesson 1.1.